Hello, welcome back to another Let's Learn Computer Science. No flag today. I know it's sad. I had to remove it temporarily for some online testing things, but it'll be up and down periodically, so we're just in a dry spell right now. For today's episode, we're going to talk about an introduction to data structures and sorting algorithms, along with some other stuff. So let's start with some problem-solving techniques. First, we're going to talk about the George Polya model. He broke it up into 4 different steps. He was a mathematician from Hungary, I believe. This is how he broke down solving complex problems. Firstly, we must understand the problem. Ask yourself, what will the solution look like? Ask yourself, what are things that I know about the problem? And then ask any remaining questions for clarity. Next, we're going to devise a plan, or for computer science, an algorithm. We're going to look for familiarities. Maybe the solution already exists. Maybe I've seen a problem very similar to this, right? Does a solution exist for the whole task or some of the subtasks? The third step is to carry out the plan and see, does the solution that I came up with solve the problem? Did the algorithm do what I intended it to do? And lastly, you're going to reflect. Does the solution have use in other problems, right? So then the next time that you use this model, and when you're in the devise a plan stage, you can look for familiarities, look for similarities with this other problem, and implement that algorithm elsewhere. Most of the time when you're in computer science, in my experience, there's an algorithm out there, there's a function, there's some code that solves what you're doing, probably in less code, more concisely, less overhead, so that's always nice. And now we're going to look at the computer problem model. Also breaks it down into 4 steps. Firstly being the analysis and specification. You can see how this coincides with understanding the problem. First, you need to define what the problem is and what is the program actually going to solve. Next, we're going to look at algorithm development. So it's devising a plan, algorithm development, logical series of steps, and check if the solution works. So here we're kind of combining the 2 and 3 from George's model. The third step in the computer problem model is implementation. Now we're actually coding the algorithm and testing the program. So for the algorithm development, let's go back to that step. You're just writing pseudocode for the most part. And then logically, with pencil and paper, you're going to walk through the logic of your algorithm and see if it produces the intended solution. And the implementation part is translating the pseudocode to actual code and testing it. And lastly, there's maintenance. Use the program, correct any errors, do your debugging, and update to meet any changing requirements, right? This is probably for like a business application or something, right? There might be changing requirements. Let's go on to the next slide here. Next, we're going to talk about search algorithms and sorting algorithms. So let's zoom on in here. So there are 2 types of search algorithms that we're going to cover today. We got sequential search and binary search. The image to the left is a binary search tree. Well, let's talk about sequential search. Sequential search works on sorted and unsorted data. It looks at every item sequentially. So an example of this would be if I gave you a deck of 52 cards and I said, find the ace of spades. And you go, nope, that's not it. Nope, that's not it. And you're just taking 1 card off the top each time and comparing it to the item that I told you to look for. That would be an unsorted data set, maybe. Maybe I shuffled the cards, let's say. Now, this works better on a sorted data set, sequential search does, because if I say look for the ace of spades, and you have that deck of cards, and you say, ace of hearts, okay, ace of clubs, okay, ace of diamonds, okay, 2 of clubs. Wait a minute, I got to the 2s before I found the ace of spades, which leads me to believe I can come to the conclusion that the ace of spades is not in this deck, because if it's sorted, and if it was in this deck, it would be right there. So sorted data works better with the sequential search. Next, let's talk about the binary search. This works only on sorted data. The binary search chooses a middle value, compares the value, and then chooses left or right, effectively throwing away half of the list each time. In this example, let's say we're searching for 4. Let's say we're searching for the number 4. And we have a number list from 1 to 15, let's say. So I'm going to pick an arbitrary middle value, 8. That's actually pretty close to the middle. And then I'm going to say, is the number I'm looking for less than or greater than my middle that I chose. So if I'm searching for 4, 8 is greater than 4, so I'm going to look at the left-hand side, and I can disregard everything on the right-hand side because that's all greater than 8, and I want to look for 4, which is less than 8. So now I'm going to pick another middle value. Let's pick 3. Okay, is 3 less than or greater than 4? 3 is less than 4, so anything less than 3 I can throw away, so I'm throwing away the 1, and now I'm going to pick the next middle value. Next I have a 6. Is 6 less than or greater than 4? Okay, it's greater than, so anything greater than 6 I can throw away, but we already threw away the 8, right? So all that's left is 7. And then you can go to the left-hand side, and what is left is your 4 that you're looking for. Binary search is by far best suited in large data sets, especially in this case where you have the data already sorted, and you can find it very quickly. Let's go on the next slide here. Sorting algorithm. So we have the quicksort, the bubble sort, and the insertion sort. So the way that quicksort works is your program chooses a pivot point, and then it figures out all the items less than that pivot point and all the items greater than that pivot point. And it splits them into their own lists. So that means that the pivot point you selected is already in the final spot that it needs to be. Let's say I have 1, 2, 3 that I need to sort, and the list that I'm given is 2, 3, 1. If I pick 2 as my pivot point, well, 3 is greater than 2, 1 is less than 2, so I'm going to place 2 in the middle. So it's already in the spot that it needs to be. But of course, we're going to be working with larger lists, so after we establish that, you have your pivot point and then the greater than and less than on these sides. Well, now we just need to do that again. We're going to do it recursively for each list until we have a bunch of lists with 1 or 0 elements. And since the pivot point is placed in the spot that it belongs in, once we have a recursive function that goes all the way down to 1 element, then we can just splice those all together, add them up into one list, and then that is your sorted list. The name quicksort is a little misleading though, because it always has to subdivide. It always has a specified number of steps, and once it gets to the end of the subdividing, then the list is sorted. There's no check condition to see if the list is sorted or not, so if I provide quicksort, a sorted list, it will still go through all the steps. Next we have bubble sort, and bubble sort works interesting. It compares adjacent elements and then swaps them if they're in the incorrect space. So if I have a 2 and a 3, I'm going to compare those. I'm going to say, okay, 2 is less than 3, so I don't need to swap those. Now I'm going to go from 3 to 1. Okay, those are in the wrong space, so I'm going to swap them. So now I have 2, 1, 3. And then I'm going to go back. 3 and 1. Okay, are those in the right spot? Yes, because 3 is greater than 1. Okay, 1 and 2. Is those in the right spot? No, because 2 is greater than 1. So I'm going to swap those. So now it says 1, 2, 3. I'm going to start at the end again. 1 and 2, are those in the right spot? Yep, no swap. 2 and 3, are those in the right spot? Yep, no swap. Oh, I'm at the end. I just did a pass with no swaps, which means that the list is sorted. So in Bubble, it does have a condition for if the list is sorted or not. That being said, you can pass in a sorted list to bubble sort, and it won't go through any unnecessary steps. It'll just check that it's sorted. So bubble sort can be useful, I guess. Usually not. And lastly, we're going to cover insertion sort. So the way insertion sort works is it finds either the largest or the smallest, whichever you want, and then places it in the correct position. So let's say I'm sorting a list of numbers from smallest to largest, smallest being at the beginning and largest being at the end. The first thing I'm going to do is look for the largest number. I don't know what the largest is going to be yet, so I'm going to see the first item in the list and say, okay, that's the largest, even though if it's not, doesn't matter, because I'm going to compare it to the next one. If it's larger, that's my new largest. If it's smaller, well, my largest is still my largest. Keep going all the way through, and by the end, you will have the largest number because you compared it to every other number. And now we can start at the beginning again and find the next largest, right? We can disregard the last item because we just sorted it. We just verified that it's the largest, and I know that the last item is going to be the largest. So you can think of it as if I have 5 items in a list and I go through and find the largest and place it at placement 5, well, now it's as if I'm sorting a 4-element list. Find the largest in there, put it at 4, disregard these 2. They're sorted. The end ones are sorted. Now I have a 3-element list. Go through there, 2, all the way down. And then by the time you have 1 element left, it's in the right spot because all the other ones are in the right spot. That's the only place it can go. Insertion seems the most intuitive to me. Some people say bubble is more intuitive, but the whole going back and forth thing doesn't really make sense to me. Those are a few beginner sorting algorithms that have their use cases. Next, we're going to talk about atomic variables. So an atomic variable is indivisible and it is a single value. Something interesting about atomic variables is that the algorithms we were just talking about cannot be performed on atomic variables because it's only a single value. What's there to sort? What's there to search for? There's nothing. A non-atomic variable is divisible. It has multiple values. It can be broken into multiple parts. These are things like lists, arrays, objects. Let's go on to the next slide. Now we're going to talk about composite variables, containers. So composite variables are non-atomic because they include multiple items or have the capability of including multiple items, because you could have an array with one item in it, I suppose. So we're going to make a distinction between records and arrays. Records are heterogeneous. They have named attributes, and an object is an example of a record. In our SQL video, our database video, those are records. Heterogeneous basically means different types of data, or data of different types. And arrays are homogeneous. They are all of the same type. If I have an array, it can only hold integers, or only hold strings, only hold characters. Can't have mixtures because it's homogeneous. Arrays are indexed, so you can search through an array by the index, by the position they're in. And an example is a list. Let's go on to the next slide. Ooh, now we're going to talk about programming paradigms. A paradigm is a pattern or a model which determines a way of viewing problems. I think of it as a programming worldview. How are you going to view reality? There are two schools of thought, an imperative paradigm and a declarative paradigm. So let's start with imperative. It is a sequential execution of instructions. It uses variables which represent memory locations, and these variables are mutable. That's why they're called variables. And you use assignment to change variables. Some examples of imperative paradigms are procedural, where you have a hierarchy of subprograms, a top-down design pattern, and object-oriented programming with active data objects which are self-referential. We'll touch more on that later. Next, we have declarative paradigms. This paradigm describes the results, but does not describe the steps. It's kind of a shift in your worldview. Some examples of declarative paradigms are functional, where you evaluate functions like a math problem, and we use recursion if we need to do a repetition. So we don't have loops. What we have is recursive function calls, a function calling itself within the function definition. And then lastly, we have logical paradigm, where you supply facts and relationships and you prompt it with questions. So I can say, John is a child of Mark, and Mark is a child of Susie. The relationships I would give, I'd say, children of children are grandchildren. So now I can ask a question, is Susie John's grandmother? And it would return yes or no, depending on the context. But in this context, it would return yes. So let's go on to the next slide. We're going to touch on object-oriented programming. Objects, which are instances of a class. They're containers. They are heterogeneous containers with defined properties and behavior. Properties are attributes. They're variables inside. They don't have to be variables. They can be constants. And then behavior, which is the methods or functions of the class. A key point about the object-oriented paradigm is inheritance, in which a derived class can use or override the features of a base class. So this like parent-child idea. An example of that would be, I have a cashier at the grocery store and a manager at the grocery store. Those are two different entities. One of them has hourly wages, one works on a salary, but they're both on the base class of employee. So they have a lot of similarities, but they're distinct enough to make them different classes. So here we can see the inheritance, where you both get an ID number. Lastly, we're going to talk about polymorphism. Any Harry Potter fans? Polymorphism is an idea that different classes can define the same method name but with different behavior. The method called is chosen based on the actual object type. So let's say the employee class has a method like getEmployeeID. Well, that would mean that the cashier and the manager could overwrite those methods with the same method name but have different behavior. It would be pulling it from the instance of their class. This can also be used to cast a cashier or a manager to an employee class. You can go up in the class hierarchy. Can't go down, though, because you don't know if you have the same attributes. Polymorphism, inheritance, all in the object-oriented paradigm. Very cool stuff. Let's go on to the next thing. Lastly, we're going to talk about the top-down design. It is a methodology involving a hierarchy of tasks to solve, in which you break down large tasks continuously into small, manageable chunks. In the process, you will solve many small known tasks to identify an unknown larger task. Maybe it's a known task, but you're solving for something that is unknown. And lastly, we're going to talk about the stack and queue. This is a data structure that I can't believe we haven't talked about yet. So we're going to throw it in here. The stack operates in a last-in, first-out manner, otherwise known as LIFO. LIFO? L-I-F-O. Last in, first out is, imagine a stack of papers. The first one's on the bottom, and they keep going up. And then the last one's on the top. But when you're picking up papers, you're not grabbing from the bottom, you grab from the top. You grab from the top. So last in, first out. You can see this being used in an undo tree for a text editor. When I undo, I want to undo the last thing I did, not the first thing I did. To add and remove from a stack is push and pop respectively. Next, we have a queue, which is first in, first out, or FIFO. And a queue works just like a line at a concert or something. The first person that gets there is the first person in, right? To add and remove from a queue is on queue and dequeue. I don't know, is that French? Too many E's in these words. But that will wrap up this episode of Intro to Data Structures and Sorting Algorithms. There's Intro to Computer Science. This Let's Learn Computer Science Together. If you enjoyed my content, please leave a like. Please comment. Have a nice day. Goodbye.